Good afternoon. We are going to start the Pedro Nunes Lecture of 2018. This is an initiative organized by CIM, Centro Internacional de Matemática, and by SPM, the Portuguese Mathematical Society, with the support of Fundação Carlos Coimbra. It intends to promote scientific research in mathematics, to show recent developments and trends, its applications and impact on different fields. Of course, this occasion is also a tribute to Pedro Nunes. This event is annual and consists of 2 or 3 lectures delivered by outstanding mathematicians that are invited to speak in Portuguese universities. This year, 2018, we have the great pleasure to have in Portugal as invited speaker for the Pedro Nunes Lectures, Professor Alfio Quarteroni. The first lecture is now. There will be a second lecture tomorrow in Lisbon, in the Academy of Sciences, and the third lecture after tomorrow in the University of Porto. Before introducing Professor Alfio Quarteroni, I would like to mention that the organization of this Pedro Nunes Lecture at the University of Coimbra has the support of CUC, the Centre for Mathematics of the University of Coimbra, and the collaboration of Gonçalo Pena. In particular, I would like to say that Gonçalo was a former PhD student of Professor Alfio Quarteroni. I would like to mention as well that Gonçalo has conducted an interview to Professor Alfio Quarteroni. This interview is going to appear in the next CIM bulletin. And this bulletin is a biannual publication whose main purpose is to promote mathematics and especially mathematical research. The next issue will be available before the end of this year in December, so I encourage you to go to the website of CIM and to look for the bulletin and look for the interview with Professor Alfio Quarteroni. So I'm going to pass now to the introduction of our distinguished guest. I will do only a short introduction because of time limitation, but this short introduction will immediately reveal the excellence of his work. Alfio Quarteroni is professor of numerical analysis at Politecnico di Milano, Italy, and director of MOX. MOX is a laboratory for modeling and scientific computing that collaborates with several research laboratories from Politecnico di Milano and other institutions belonging to industrial and academic world. He is the founder of MOX at Politecnico di Milano in 2002, the founder of multiphysics at EPFL, the Swiss Federal Institute of Technology in Lausanne, in 2010. He is also the co-founder and president of MOX-OFF, a spin-off company at Politecnico de Milano, in 2010. He is also the co-founder of two recent startups, companies, Mathesia in 2015 and Math and Sport in 2016. He is a member of the Italian Academy of Science. He is a member of the European Academy of Science and a member of Instituto Lombardo di Scienze e Lettere. He was director of the chair of modeling and scientific computing at EPFL in Lausanne, Switzerland, from July 1998 until December 2017. He is author of 25 books, editor of 5 books, author of more than 300 papers published in international scientific journals and conference proceedings, member of the editorial board of 25 international journals, and editor-in-chief of 2 book series published by Springer. Among his awards and honors, we mention the NASA Group Achievement Award for the pioneering work in computational fluid dynamics in 1992, the Fanfolino della Riconoscenza in 2006, the Prêmio Capo d'Orlando in 2006, the Guillieri Prize in 2013, the International Galileo Galilei Prize for Sciences in 2015, and the Euler Lecture in 2017. He has been invited speaker at ICM, the International Congress of Mathematicians, in Beijing, China, in 2002, and plenary speaker in Madrid in 2006. His research interests concern mathematical modeling, numerical analysis, scientific computing, and applications to fluid mechanics, environment, geophysics, medicine, and the improvement of sports performance. In particular, his group has carried out the mathematical optimization of the early solar impulse, the airplane propelled by solar energy. He is the recipient of several European Research Council grants. I'm just going to mention the last one, obtained in 2017, the project I Heard, in the framework of the European Union's Horizon 2020 Research and Innovation Programme. Finally, I will close this brief introduction by mentioning another award and an achievement of Professor Alfio Quarteroni that somewhat illustrate the connection with Pedro Nunes' work. As we all know, much of the work of Pedro Nunes was related to navigation. So, Professor Alfio Quarteroni is Doctor Honoris Causa in Naval Engineering from the University of Trieste, Italy, in 2003. The group, and the other achievement, the group of Professor Alfio Quarteroni has carried out the simulation for the optimization of performance of the yacht, a kind of a boat, that was the winner of the America's Cup in 2 editions, in 2003 and 2007. So these two achievements are a perfect connection with the work of Pedro Nunes related to navigation. So Professor Alfio Quarteroni, it's a pleasure to welcome you to the University of Coimbra. You can start your lecture here in this room, that is the Pedro Nunes room, and in this university where Pedro Nunes was a teacher of mathematics, intended to provide instruction in the technical requirements for navigation. Thank you.
Okay. Good. I can put there. All right. It's easier. Okay, thank you.
Thanks. Thank you very much for this beautiful presentation. I'm, of course, very honored to be here today to open this series of lectures, of Pedro Nunes Lectures, in this great and historical room. It's a big honor and also a big responsibility, I have to say. So I'd like to, first of all, thank all the institutions that are behind these lectures, and then more in particular and more specifically, Isabel and Gonzalo for having been so kind and so generous, assisting me and helping me in solving all practical problems. So thank you for coming. Today I will talk about a kind of specific mathematical subject. Tomorrow we'll talk about a more general issue which is concerned with the modeling of the heart and all its implications also with real life. Today we'll talk about multiphysics, a method for multiphysics. And before starting with mathematics, I would like to give you a bit of a flavor of what a multiphysics problem is. Well, just to oversimplify, you can think of a problem that is set in a certain region of the physical space or three-dimensional space. We'll see then in my examples what this region will represent actually. And at the abstract point of view, the abstract level, you can think of having this region split into two regions. And in the two regions, there are different types of physics. Say this is one type of physics, physics 1, and this is another type of physics, physics 2, say. And for us, the mathematician, this means that you have a partial differential equation of a certain type here, and the partial differential equation of another type here. So the problem is how to couple these two partial differential equations through the boundary. This is the boundary, let me call it gamma. Actually, it's not a boundary, it's an interface between the two regions. So I go to talk about methods that are suitable, mathematical methods, numerical methods. Actually, I'll see them before the mathematical level, a differential level, and then the numerical level, that are suitable to couple this type of physics, two types of physics, in a very abstract way. So I will start by showing some examples, and you already see the numerical solution of those type of problems. So we'll see just the end of the story, right? But this is just for the motivation. And then I will come back to make a very quick abstract illustration, and then again I will go back to show the numerical approximation. So to have examples that you can deal with, we can start with this example, for instance. You see this is a bridge. It's a bridge and there is a train going on this bridge. So it's a railways actually. And the question is whether or not this bridge will resist an earthquake, for instance. This is a bridge in a region that is sensible to earthquakes. There are many different types of bridges like that. Portugal, luckily, is not very much exposed to earthquakes, but places like Italy, Turkey, Greece, Japan, and many, many others are much more exposed. And so what is the problem here? The problem is that we like to see whether or not this bridge will resist an earthquake. An earthquake is a seismic wave that propagates from a point beneath the soil, and then it propagates through the soil. And this is one physics, right? So this is the soil, so you have this wave propagating, and then gamma is the surface of the Earth, where you have buildings, in this case, a bridge, say. And what you have in this other region, you have a bridge, and you have another model that describes the behavior of a bridge, of the structure, when you have an external solicitation, say. So this is the multiphysics problem in this case, right? So this is the bridge. Now you see the wave coming on the terrain, and of course the bridge will shake because of the fact that you have this seismic wave that will impact the bridge. So literally speaking here, gamma is just the union of those pieces here, right? Those pieces here, where you have the separation between the bridge and the soil. So this is just the simulation, and this in particular is what you see in the bridge, right? This is three-dimensional computational mechanics, while in the soil you have waves that propagate from a given point, actually a fault. You have a sliding fault, and then your propagation of waves. So this is one example of multiphysics, and the two physics are, again, computational solid mechanics and seismic wave, propagation of seismic waves, say. This is a second example, totally different. This is an arterial vessel. Actually, it's called the carotid. The carotid, we have it in our neck. We have two of them, one on the left and the other on the right. And there's a bifurcation. And one branch goes directly to the brain, you see, and feeds our brain with blood. And the other branch goes to the face, and it provides blood and therefore nutrients to our face, right? So what we see here is fluid. This is blood flowing into the vessel, and then you have the deformation of the vessel itself. So this section here and there, these are the cross-section of the vessel, and the vessel is a material, a smart material indeed. So in that specific case, you need two types of problems, two types of physics. You have an equation describing the blood motion. In that specific case, this would be the Navier-Stokes equations for fluid dynamics. And then, this is in the lumen, and then you have here an equation of elastic wave propagation in a smart material like this one, which is actually a multi-layer material. And of course, the interface, gamma, is the endothelium interface. So it's this area, which is the innermost part of the vessel, say. This is another example, which has to see with heart. These are two cavities on our heart. So our heart has 4 different cavities, 2 ventricles and 2 atria. And in this specific case, you see the left heart, the left ventricle, and the right ventricle. Those cavities are occupied by fluid, blood in this case. You don't see the fluid here. We are only solving the electromechanical problem. So our heart beats because at every instant, every second of our life, you have a source of electricity that is providing a specific point of our heart, and then it propagates, it generates an electrical field that propagates and involves every single cell in our heart, every single myofilament, and the myofilament will contract and relax under this action, and the global action, the aggregate result of this contraction and dilation of every single myofilament provides the dilation and the contraction of the heart itself. So what you see here is just one snapshot of the contraction of the heart at different instants. This is at one instant, this is another instance. And you see different colors. The colors in this case refer to the different displacement that you have. So in this specific case, you are solving a multiphysics problem. You have 2 different types of physics, which are, however, coexisting in a different domain. So the framework is a bit different than this one. You have electrical propagation, so you have the equations for electrical propagation that are suitable to compute the electric potential, and then you have the mechanical deformation. So this is an electromechanical multiphysics problem. Right? This is still the heart. Now you will see here the upper part, which is the left atrium, and the lower part, which is the left ventricle. And in this case, we'll see it now. And in this case, you'll see the fluid structure multiphysics problem, namely the interaction between the fluid in the ventricle and in the atrium and the mechanical deformation of the ventricle. So this is a healthy heart. You see here the time, we go from 0 up to 5 seconds, more or less. So these are 5 heartbeats, and you see the way blood flows from the upper atrium into the ventricle. You see here 4 veins that are providing blood, oxygenating blood from the lungs, and the blood enters this upper part, which is the right atrium. Then when the pressure is high enough to win the resistance of this valve, which is the mitral valve, then it goes into the ventricle, the left ventricle, and when this contracts, and when this contraction wins the resistance of another valve, which is the aortic valve, the aortic valve opens up and blood is ejected into the main aorta. So this is fluid and structure interaction. So one domain is carrying the fluid part. This is the internal part of the lumen, the internal part of the atrium, and the other domain is describing the deformation of the external tissue, which is the myocardium. The myocardium, the muscular part of our heart. So these are few examples where you see that you have often, in many different contexts, interaction between 2 different types of processes that you want to model mathematically and solve numerically. Okay, so this was just motivation. Now, before going on, well, this is yet another. Why not? Now you have wind, and you have a sail that is deforming. So again, you have external fluid dynamics, and then you have deformation of a thin shell, if you want to solve the problem by a thin shell, or again with a 3-dimensional structure, if you want to simulate or model the sail by a 3-dimensional model, say. I'd like to now to move to mathematics and try to explain a possible way to address those type of problems in a general framework, in an abstract way, say. So this is my target problem. And before moving there, I would like to show how you can deal with a similar problem, not for a multiphysics, but for a single physics. So we're going to learn a lot on a problem which is run by a single partial differential equation, and then we see how this approach can be turned useful for 2 different types of partial differential equations. So let me call this a single physics problem. Single physics problem. Now, if we want to oversimplify everything, you can just think of a simple elliptic equation, elliptic partial differential equation, just to oversimplify. Okay? So the example is minus Laplacian of u equal to f in omega. So it's a steady problem, while all those problems that have been shown before were non-steady. But this is a detail somehow, right? So you have the Laplace equation in a given domain, omega, this one, and the plus boundary condition. Boundary conditions here do not play any role. These are the boundary conditions, the external boundary. So you don't even write them, right? This is in omega. Okay, so this is my domain, omega. Could be a 2-dimensional domain, a 3-dimensional domain. There's not really a difference. And for some reason, I decided that I want to divide this domain into 2 subdomains. This is pure mathematical speculation. There is no physical reason for that, okay? So let me try to draw an interface here between 2 subdomains, omega 1 and omega 2. You have the same type of problem. For instance, if this is an elastic membrane, this is the displacement of the elastic membrane, right? Same type of physics. But mathematically speaking, we want to see the problem in this way. Okay, how can we reformulate this problem here, which is a single domain problem, into a problem which is a 2-domain problem? But we want to end up with something which is purely equivalent. So at this stage is pure mathematical speculation, okay? This is not a big deal. You have many different ways, but let me show you the 3 of them. Because these 3 methods will stand at the basis of the numerical method that I'll explain later on, and which will then be applied to the multiphysics environment. Right? So this is my original problem, right? In a domain omega. So this is a possible way to solve this problem in a domain which is split into two subdomains. Here you have two rectangles, but this does not matter. Okay? So this problem is equivalent to solve the same problem in the two subdomains and enforcing these two conditions at the interface. U1 is equal to U2, so U1 is the restriction to omega 1, U2 is the restriction to omega 2. Right? U1 is equal to U2, and the normal derivative of U1 is equal to the normal derivative of U2 on gamma at the interface. So those are called transmission conditions at the interface. The two problems are equivalent. It's very easy to show this by variational methods, say. You solve it, you frame everything in the subword space H1 or H10, and then by variational formulation, you end up with showing that these two things are equivalent. This is very classical. You can find it, for instance, the book by Lyons. So this is absolutely very classical. Those are called by Lyons himself, Jacques Lyons, transmission conditions at the interface. I will not talk about that today. However, this reformulation stands at the basis of a big family, successful family of domain decomposition method for solving partial differential equations. These are called the sure domain decomposition methods. Sure-based domain decomposition methods. They are all derived by this type of formulation. Okay? Now, just to make things clear, I'm talking about two subdomains, but if I'm going to divide it into hundreds of subdomains, things should be the same, right? At the interface, you will have this type of transmission conditions. And why am I talking about hundreds of thousands or millions of subdomains? Because if you want to solve problems by parallel computing, you have a multiprocessor machine, a machine with many different, say, brains, CPUs, then you want to split our problem into many different subproblems. This is pure mathematical speculation, just for the sake of computational efficiency. Okay? But to explain the mathematics behind, let me just stick with two subdomains. Right? So this is one approach, based on transmission conditions. I will call this approach the sharp interface approach. This is a partition, is a disjoint partition. Right? An alternative is to use a non-disjoint partition like this one. You see, you have one domain, omega 1, and then another domain, omega 2, that overlap. And then I have gamma 1 and gamma 2 that are the two boundaries of omega 1 and of omega 2, respectively, and omega 1, 2 is the overlapping region. Can you set up an equivalent formulation for the Laplace equation in this context? Yes, this is one possibility. You again solve the same problem in omega 1 and omega 2, and besides, you look for the continuity in the whole region omega 1, 2. So you pretend U1 and U2 to be continuous, to be the same, actually to be the same in the whole overlapping area. So you can show that this is equivalent to the original problem. Is there any reason to end up with this type of overlap? No, theoretically speaking. No reason, theoretically speaking. But you'll see this will be very interesting from the numerical viewpoint. Okay? And this is a third equivalence theorem. So you can still work on this overlapping structure and enforcing this time the continuity only at the interfaces gamma 1 and gamma 2. Instead then enforcing the continuity on the whole domain, on the whole omega 1, 2, you just force the continuity in gamma 1 and gamma 2. And still you recover the same solution. In the sense that in all those cases, U1 is the restriction of the true solution in omega 1,